These are the notes for standard 2.7, which are two-dimensional projectiles or projectiles that are thrown at an angle. So in this standard, we will be considering the components of an object's velocity separately as an x component and a y component, but specifically the initial velocities of objects in these problems will be at an angle, and so what we'll have to do is decompose them into their horizontal and vertical components using some trigonometric ratios. Here you'll see that the red component, which is the x component of the ball, stays the same size the entire time because it's moving at a constant velocity in the x direction, but the green arrows, which signify the vertical component of the velocities, first change size and then ultimately change direction because they are affected by gravity since they are vertical. So we've got two example problems. In the first example, we have a ball that's thrown 30 degrees above the horizontal at 25 meters per second. If it's released from a height of 2 meters, we have to find how long it will be in the air and how far it will land away from the thrower. So here's a diagram of the situation with all of the given values from the problem in it, including what we don't know, which is how far away the ball is going to land. Notice that we put a little dotted line here for the horizontal, which will help us to start picturing this initial velocity as a triangle, because if we picture it as a right triangle, then we'll be able to split it up into components using trigonometric ratios. The givens are the angle that it was thrown at, the total initial velocity, the height that it started at, and the acceleration due to gravity, which is negative 9.8 meters per second squared. And what we don't know is how long it will be in the air and how far away it will get. Now, the biggest difference between this standard and the last standard is that we want to be able to take this given velocity that is no longer just horizontal or just vertical, and we want to split it into two components, into its horizontal velocity or its x component and its vertical or its y component. So to do this, what we need to do is look at this as a triangle with two components and a hypotenuse. And use the angle that's given to us in trigonometry in order to solve for these legs. And so if we're considering just this x component, the useful trigonometric ratio would be cosine, which would compare the adjacent side and the hypotenuse. If we rearrange this equation, we multiply both sides by the total velocity or the hypotenuse, and we get that the x component is equal to the total velocity times the cosine of the angle. The same thing can be done with this component, which is opposite of the angle, and so we'll be using sine instead and see that that leg is equal to the hypotenuse times sine of the angle. For this specific problem, we have a hypotenuse of 25 meters per second, and the angle that's given is 30 degrees, and so the x component is 25 times the cosine of 30, or 21.65 meters per second, and the y component is 12.5 meters per second using sine of 30 degrees. So now I've included these two velocities in our givens because we just calculated them using this information. Notice that I also included arrows to help us keep track of what direction these velocities are pointed, so that it really can help us to keep track of which equations the velocities can fit into. So for our horizontal equation, we've got a constant velocity equation that only relies on the initial velocity in the x direction. And for the vertical equation, we have an equation that takes into account acceleration due to gravity and the initial velocity in the y direction. Because we know where it's starting, which is at 2 meters, and where it's ending, which is at 0 meters, we're going to rely on the vertical equation first, plug in the acceleration due to gravity and the initial velocity in the y direction, and then solve for time using the quadratic formula, which tells us that it would take 2.7 seconds for this ball to reach a height of 0, which would be the ground. Then what we can do is we can use that time and the initial velocity in the x direction, and we can multiply them to find how far along the ground the ball would get in this time frame, and that would be 58.5 meters, which is how far horizontally away the ball will land. For this second example, we have a BMX cyclist who attempts to jump from one building to another. They leave a 40-degree ramp on the top of a 15-meter building at a speed of 8 meters per second, and the closest building is 12 meters away. So we want to find how long the cyclist is in the air, and then what the maximum height of the second building could be, which would allow the BMX biker to still safely execute the stunt. And so here we have a diagram of the situation with the separation between buildings, the initial velocity, and the angle that the cyclist is traveling at when they leave. Here's a list of our givens and the two things that we don't know, which is the time that they're in the air and what that final height could be for them to safely execute the stunt. So similarly to the last problem, what we need to do is split the total velocity of 8 meters per second into two components, an x component and a y component, using this 40 degrees. And so we did that here using cosine of 40 degrees for the x component and sine of 40 degrees for the y component. Now that we have those, we can use a horizontal equation since we know where they are starting, which is at 0 meters, and how far they need to go, which is 12 meters horizontally. We're also relying on the x component of the velocity in order to solve for the time of 1.96 seconds, which is how long that they'll be in the air. And then for the maximum height, we'll rely on the vertical equation since the maximum height is the final y position. And we can plug in the acceleration due to gravity, this time that we just found using the horizontal equation, the y component of the velocity, the time again, and then the initial position of 20 meters. And we can solve that when they are that far horizontally from the building, they'll be 11.28 meters above the ground. And so any building that was 11.28 meters or lower would be able to be landed on by the BMX biker, but if it was taller, then the BMX biker would not make it. And so here are the same tips as from standard 2.6. With one additional, which is be attentive to which direction the velocity components are in, especially seeing as you are given a total velocity and then an angle in order to calculate the initial x and initial y velocities. And so if something is being thrown down and to the right or up and to the right, it's always a good idea to draw that triangle made up of the total velocity, the x component of the velocity, and the y component of the velocity in order for you to keep track of which direction each component is in and whether or not it deserves to have a positive or negative symbol in your calculations. Thank you.